Here is man in an unearthly environment, weightless, 100 miles out in space. His speed of 5 miles a second is pulling him outwards. Gravity is pulling him in, so he's held in a curving path around the Earth. Here is man in a new role. For these few minutes, he is himself a satellite. Man's achievement in orbiting a spacecraft is only a few years old. But the laws that govern how a body moves in space are as old as the universe itself. And we've understood them for quite a long time. Back in 1687, Newton worked it out in theory. Now, he reasoned that if you could somehow hurl an object at just the right speed, and what was very important, hurl it above the resistance of the Earth's atmosphere, then it would stay in that circular orbit, going around the Earth forever. He also understood that when it was launched, it had to be moving horizontally to the Earth's surface. If it were going straight up, then the force of gravity would just slow it down and it would fall back down to the Earth. Now, Newton's mathematics gave him the precise speed needed for a circular orbit. But it's just about impossible for a real rocket to get that precise speed for a circular orbit. So most real orbits end up in what's called an elliptical shape. That is, they're further away from the Earth on one side than they are on the other. The planets move around the sun in elliptical orbits, and the moon moves around the Earth in an elliptical orbit too. Here's the launch vehicle, rising slowly at first through the densest part of our atmosphere. Half its fuel has gone now. It's lighter. It's going through thinner air, meeting less air resistance. It tilts, flies parallel to the Earth. A final boost speeds it up to more than 17,500 miles per hour into orbit around the Earth. As the satellite moves out, gravity steadily slows it down, so that finally it is moving so slowly that it can no longer resist the force of gravity. It has gone as far from the Earth as it can. This point on the orbit is called Apogee, or the far point of the orbit. Then it begins moving back down toward the Earth in a long, looping downward curve. It picks up speed as it goes, until finally it whips around this portion of the orbit, moving so fast that it can go back out again on the same elliptical path. This point is called perigee, or the near point of the orbit. If the satellite meets no air resistance to slow it down, it will stay in orbit indefinitely. If it does go down through a little bit of the Earth's atmosphere here at perigee, then it will be slowed down just a little bit. It won't be able to get out quite so far on the next orbit. It won't be able to get out to the same apogee. Each time it goes around, it will be slowed down a little more, and each orbit will be a little smaller. Scientists call this process orbital decay. Finally, the whole orbit is inside the atmosphere. What happens then? Well, the satellite can't keep going fast enough to stay in orbit, but it's still going several thousand miles an hour. As it rushes through the atmosphere, it compresses the air in front of it, and the compressed air gets hotter and hotter. This great heat is transferred to the satellite that's pushing against the air. It begins to get hot too. It gets red hot and white hot, and unless it has some special heat protection, it will burn up. To get a satellite into an orbit that will stay above the atmosphere, we needed powerful rockets. And we needed to perfect a new idea called staging, placing one rocket on top of another. In the 1950s, we were testing the Redstone rocket, a midget compared to our modern moon rockets, but in those days it was one of our largest. Dr. Wernher von Braun was one of a group of scientists who wanted to modify the Redstone, add other rocket stages on top, and use it to launch a satellite. Their tests seemed to show that it could be done.
At 34 minutes after the hour.
However, a decision was made to build a new rocket, the most advanced rocket of its time, the Vanguard, built to launch an artificial satellite in 1957. 1957 was the year of the first Earth satellite, a Russian satellite, a 184-pound metal sphere called Sputnik 1. It radioed back to Earth the first signals from space. One month later came Sputnik 2, 1,000 pounds this time. It even carried a dog, the first space traveler. And the new Vanguard didn't look as if it would ever get off the ground. The Russian accomplishment amazed the world. Many people said that we should be working together, not as separate nations, but as mankind against the unknown. Other people spoke of the space race, and Russian satellites were up there. So the question was why? And the answer went back to the time when the Russians were building rockets to launch their first nuclear bombs. These early bombs were big and heavy, so the rockets to launch them had to be very powerful. This meant that the Russians had large, powerful rockets with which they could launch very big spacecraft. Our rockets were comparatively small because we had chosen big airplanes for national defense. When the space program began and rockets were to be used for peaceful purposes, the Russians had big boosters ready to go. American engineers had some hard work ahead of them. The first job was to launch a satellite. 80 days after Sputnik 1, America launched its first satellite, Explorer 1. A modified Redstone put it into orbit, just as von Braun had suggested. Vanguard 1 and Explorer 3 followed, making 5 Earth satellites in just 6 months. Now we could send up satellites to get information we could never get before. The satellites radio the information back by telemetry. Telemetry changes the small movements and signals from measuring instruments into an electronic code. The instruments might be measuring temperature, or counting meteorite hits, or taking photographs. Even photographs can be changed into a code. When relayed, it looks like a series of numbers. Computers change the code back into photographs. Telemetry reports from early satellites told us the Earth was surrounded by huge donuts of solar radiation, the Van Allen belts. Chemical batteries run down too quickly in space. So we developed solar batteries. These are the shiny silicon cells you see on the outside of many satellites. They convert sunlight into electricity to power the instruments and the transmitters on board. Now we use satellites every day. Big storms cause fantastic damage each year. When we know ahead of time that big storms are coming, we can prevent some of the damage. If we could learn why they happen, we might even be able to stop them. Weather satellites send us pictures of the Earth and its clouds from 500 miles in space. From this, we can learn more about the changing weather patterns. Satellites also report on the activity of the sun. Knowing how the atmosphere absorbs solar radiation is vital to understanding how our weather is formed. We use satellites to send radio and television around the curve of the Earth. The first communication satellite was Echo 1, a huge plastic balloon. You're watching it being inflated in space. Radio signals were bounced off its surface. Today's communication satellites carry their own receivers and transmitters. In 10 years, more than 600 satellites were sending us messages from the space around us. Getting our first satellite into orbit was hard enough, but getting our first man up there was an enormous undertaking. There were many things we didn't know. What would happen to an astronaut in the acceleration after liftoff? We knew he would be subject to very powerful forces. How would he react? There were many people who felt he would be helpless, unable to do any work. Then there was the problem of weightlessness. We could do tests in airplanes for a minute or two, but no one really knew what would happen to a man in space. Our astronauts went through extensive training and medical testing to see if they could withstand the rigors of space. Most important, what about the feeling of being alone up there? What would that do to a man's mind? We set about finding the answers with the Mercury program. Our first astronaut was Ham, a chimpanzee. He tried out the capsule, taking acceleration and reentry pressures successfully. In 1961, a man orbited the Earth for the first time, a Russian cosmonaut, Yuri Gagarin.
Кетер, я заря 1, зажигание.
Понял, дается зажигание.
Желаю вам доброго полета.
Я заря 1, мы все желаем вам доброго полета, все нормально.
Now we all knew man could travel in space. He could survive the strain of getting up and getting back. Two American test flights launched astronauts in the new Mercury capsule from Florida eastward to the Atlantic Ocean. The first American went into orbit the following year. The Atlas was the booster vehicle, the little Mercury capsule perched on top. John Glenn squeezed into the capsule, and the final countdown began.
Minus 40.
Status check, pressurization.
Go.
Locks tanking.
Have a blinking high level light.
You are go.
Order
Order
systems.
retract
now.
Range operations.
Right there.
Mercury capsule, go. All pre-start panel lights are correct. The ready light is on. Eject Mercury umbilical. Oil evacuate.
Mercury umbilical clear.
Mercury is go.
Evacuate, lights on.
All recorders to fast. T-minus 18 seconds and counting engine start.
You have firing signal.
Good Lord, ride all the way.
Godspeed, John Glenn.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
We all shared the tension of that flight. Just before reentry, we thought the heat shield might have slipped. We were afraid there was something wrong with the retro rockets. But everything worked. The machines and the people did just about everything they were expected to do. And we honored a new hero, John Glenn. The following Mercury flights were longer, and they confirmed that man could live and work in space. The Russian and American manned space programs had very similar goals. They duplicated each other. But the Russians did many things first. Orbiting the Earth, two-man spacecraft, Valentina Tereshkova, a woman in space, spacewalks,
Есть держать площадку.
Back in 1961, President John F. Kennedy had promised that we would land a man on the moon by 1970. And to do this, we had to take several steps. We had to build a very powerful rocket. We had to build bigger spacecraft. We had to learn how to adjust the orbit of a spacecraft and how to join up one orbiting vehicle with another. The Mercury flights had shown us man could be a space passenger. The Gemini program would tell us if he could be a space pilot as well. Orbit changes, rendezvous, docking or joining two spacecraft together, these were the important elements of the Gemini story. Here is Edward White walking in space.
It looks like there's a coating on the outside, and you've rubbed it off. That's exactly what you've done. Now the spacecraft rates are up about 1 degree per second.
in pitching you on about ½ degree per second in roll.
I'm not that bad at the pitching that I've got yet.
Okay.
Here are Gemini 6 and 7,
Would you continue with the description of your
one
lead?
being photographed from the other.
Right now, 6 is about 10 feet above it to the left.
They're moving at 17,500 miles an hour. The pilots are flying them to within 18 inches of each other.
Able to see in the windows of 6 very easily and vice versa? Roger, 7 here. Roger.
This was the mission that many people think was the turning point in America's space effort.
Roger, Jim.
In the Gemini 9 mission, the astronauts rendezvoused with a target vehicle they nicknamed the Angry Alligator, but no docking could take place. Gemini 10 successfully docked with the Agena target vehicle and fired the Agena's engines to propel it into a higher orbit, an important maneuver in a moon mission. Less than 10 years had gone by since we put up our first little Earth satellite, and now we could put men in orbit. We were ready for the next great adventure. The Apollo missions and the moon. And that's the next part of our story.